So, as I said, this is modular parametrizations 2. And then it's the end of the parametrizations. So I want to talk about some properties of these parametrizations once we know that they exist. And so I want, so the first part is about strong parametrizations. And Stevens's conjecture. This is Glenn Stevens from Boston University, I think. I will give a detailed reference to that. So the point is the following. If we start with an elliptic curve over Q, then there is a unique strong curve associated with this. So let N its conductor. Then there is a unique E prime actually sitting inside this Jacobian that is isogynous to E. So isogynous over Q, there I mean. So the question that poses, that one should ask in this case, which curve is this, right? Which curve E prime is this? So maybe I should recall a little bit how one makes this E prime. So suppose that, so this is between parentheses, if I have phi a modular parametrization of this E, then this gives me a phi upper star, so to speak, from E to J0n over Q. And the image of that is this E prime. Right? So the question is, how can we see so a lot of times it happens that an isogeny class over Q of elliptic curves has just one element. Then of course you don't have to ask this question because it's obvious. But if there are more curves in this isogeny class, then one of them is the strong one. And the question is, can you say which one it is? And the answer is that we don't know so well. I mean, there is no, so there is this, so answer, not so clear. So just to give an example, let's look at the smallest conductor where there do exist elliptic curves. This is at a conductor 11, right? Then you have, if you look in these Antwerp tables or Cremona's tables, there are three curves called 11A, 11B, and 11C. So, and what is it?
11A1, 11A2, and 11A3.
Where? In which table? In Cremona's table. This is Antwerp 4 language. I'm old, you know, so. Okay, so Antwerp 4 language here, right? And this one is X111 over Q. So this happens to have for once the same genus as X011. And this is just another one, and they are isogynous by isogenies that we understand in this direction. So gamma 1 of n is a subgroup of gamma 0 of n. So this is only logical that this one is a quotient of this, right? And it's an isogeny of degree 5. And this is also an isogeny of degree 5, and this is the quotient by the subgroup generated by the differences of the cusps. So there are two cusps, and the difference has order 5, and you get this quotient. So, of course, this is the strong curve in this isogeny class, but it's not the best curve in there, actually. If you write down the equations, you see that this has an equation with smaller coefficients, a global Weierstrass minimal equation over Z. So this one looks nicer. And it's not just, so there is one thing by which you can measure how complicated an elliptic curve is. It's called the Falting's height. So 11a has the smallest Falting's height. I think this is not going to be part of Oosterlee's lecture because this is not in the Birch-Finit and Dyer formula, right? So I'll say something about this. But so there is this proposal by Glenn Stevens in an article in Inventiones in, what is it, number 89, and this was in 1989. What does he say? He says the following, that there is a better question. So here we had a question, which is the strong curve in the isogeny class. The better question is replace x0 nq by x1 nq. That's what he proposes. Actually, he proposes something. This is a very serious person. He says, well, anyway, what is this kind of ad hoc method to parameterize elliptic curves by x0n? That's not natural at all, because you have lots of congruent subgroups in SL2 of Z. So, and actually you should work with GL2 and not SL2 over the adelics. But so we should look seriously at all the congruent subgroups and then choose what we want to take. And so what he really works on, he studies what happens with these parametrizations as you just look at all the congruent subgroups. And what he shows is that the notion of this strong one stabilizes at x1 of nq. So you can also take modular curves that dominate this, but then you will always find the same elliptic curve in the Jacobian of those curves. So that's a very nice thing. And it is much more natural to work with x1 of n than x0 of n. So one should say almost that working with this x0n is a kind of historical error that only makes things look more complicated. Maybe if you work on a computer, then x0n is smaller than x1 of n, right? So you could do this, but you should be aware that you get better answers to your questions, simpler answers to your questions if you work with x1. So this is what he proposes, and he really proves that x1 of n is the right thing here. So the conjectural answer, so the answer is not really proved, but it has been tested in a lot of cases. The conjectural answer to the question in this case is that E prime, say E prime prime, right? So this gives me an E prime prime inside J1 of nq, the modular curve, I mean inside the Jacobian of x1 of n. E prime prime is the curve in the isogeny class of E with the smallest Falting's height. So now I will tell you what this Falting's height is. Right, so basically you should think about just that it has the smallest coefficients if you write down a global minimal equation. But maybe before I say that, I want to say a bit more. there is also a theorem that he proves. So this is also Stevens. So what does he prove? Each isogeny class of elliptic curves over Q contains a unique element with minimal Faltings-height, but because this is not even clear from the start. Faltings-height. And then you can even say, and that one is even, you can also characterize it in another way. That one admits a tau isogenies, so I'll have to say a bit what this means, isogenies to all the others in its isogeny class. So somehow all these curves are isogenous, and by a tau I mean if you extend over Z to neuron models, right? So this is, so this morning there was a neuron model, right? I don't have to explain that. Oops. Well, let me just, all those on neuron models. Over Z. Okay, so that is, so this is something that he points out also. I mean, if you're really more, you can even be more serious than Stevens and also ask what happens if you replace Q by something else. Then this goes wrong probably. This is not, you cannot do something like this over number fields. But so in the proof at least that of this theorem uses very much that this is everywhere unramified, right? So that it is Q. So what should I say, right? Neuron models, we have seen this morning what they are. I mean, this has been explained a bit. It is a bit the best possible extension of an abelian variety over a Dedekind scheme, right? If you have it over the generic point, you somehow take the best possible model over this Dedekind scheme. Now, the height of an elliptic curve. So for E over Q, we have let E of Z be its neuron model, right? We have seen this morning that this is, it exists and is unique up to unique isomorphism, so we can talk about it. So then we can look at the following thing. So this E of Z is, it's still a curve over spec of Z. It is a group. It's a group scheme. So we have a zero section, and we can get from this zero upper star of the relative differentials is a free Z module of rank 1. So that is good, because then it's isomorphic to Z. And there is some choice, there's something canonical you can choose. This is a generating differential form, right? Up to a sign, this is unique. So we get, let omega, now I do something very, not so very canonical, omega E be one of the two generators. So it is unique up to sign. And I can also view this as a translation invariant differential, actually as a differential form, say. Differential form on E of Z, right? Because, so what I say is I pull this back at the zero section, so that means that I get the cotangent space at the origin. But if I have a basis for that, I mean, I can also, at every point I can make a trivialization. I get a translation invariant differential form. And actually you can prove that all the differential forms on there are translation invariant. So it's just the same thing as the, so why don't I write this down? This is the same as H0 on E of Z of omega 1 of E Z over Z. It's the same thing. So we have this differential form, and the Faltings height of E is what you can say it is the Arakelov degree of this 0 upper star of omega 1 Ez over Z. Then I would have to explain what this Arakelov degree is, but I don't want to do this so much. I just say, okay, you get minus log, or what is it? There is a half also. Let me see. Yeah, minus 1/2 log, and now you get yeah, so let's say I over 2 times the integral over the complex points of omega E wedge omega E bar. Right, so this I over 2 is just to make this like dx dy. And in a sense, what is here is just the volume, the co-volume, if you want, of the period lattice. Lattice of E with respect to omega, to this differential form. Right? You can integrate this differential form over the 2 cycles you have. Then you get a lattice in C, and it's just, you can take the volume, the area of this lattice, and this is what you get. This is the Faltings height. So, so this is actually a very nice conjecture. I mean, it's just a very good intrinsic characterization of what the strong curve should be. Maybe I should also say something about these étals, about this theorem of Stevens. So if I have, say, an isogeny phi from E1 to E2, an isogeny over Q, right? Then you can check that. Then phi extends to, say, still denoted phi, to the neuron models over Z. And this extension is a tau, unramified, say, is a tau if and only if phi upper star of the omega 2 of the omega of E2 is plus or minus the omega of E1, right? That is so these Néron differentials are important, right? And one reason to speak about it is that this is part of the Birch-Minot and Dyer conjecture, this Néron differential. Right? If I look at, well, I saw the conference schedule, and it was somewhere in a color, right? It was a so this theorem is very nice, and I repeat that I think it's a historical error to work with x0, because this really shows that this x1 has better properties. Also, you can say, okay, but how much is the difference, right, between these two things, right? What is the, if we really want to work with x1, how much of the results for x0 can we use? So, okay, so I'll say that in a moment. There is a recent result. Maybe I should, yeah, before I do that, about this Néron differential. If you don't know this, so if y squared plus a1xy equals plus a3y equals x cubed plus a2x squared plus a4x plus a6 is a global minimal Weierstrass equation for E, all right, for your elliptic curve, then you can take omega E is dx over the derivative with respect to y. So that would be 2y plus A1x, right? Plus A3. So there is you can just do this, right? so just to make things explicit. Okay, so there is a result by Naik-Vatsal, or actually, his official name is with a V, right? Vinayak. Okay, good. So, but he signs like this. So what is he? This is a preprint of February 2002. You find this preprint on his homepage. It says that if E is semi-stable, this is a notion that Oosterlee hasn't mentioned yet, right? So I should say, I can say this in two ways. I can say n of E square free. Equivalently, no additive reduction, all right? So you know that if you a minimal Weierstrass model can have a few possible type of reductions. You can have a good reduction, well that is good, because then that prime does not occur in the conductor. You can have multiplicative reduction, split or not split. In that case, the prime exactly divides this conductor, and you can have a cusp in which p squared divides the conductor, but there can be more factors p. Right, so semi-stable means that actually you can also say that this Néron model has fibers at every prime, and Oosterlee described the possibilities for the connected component over the algebraic closure. He said this is an extension of an abelian variety by an extension of a torus by a nilpotent group. Well, in the case of the dimension is 1, you can exactly have one of the three types. You can have good, multiplicative, or additive, right? So that is the, so if E is semi-stable, then what? Then Stevens's conjecture is true up to something, up to an isogeny of degree or power of 2. So that already means that it is almost, I mean, for the semi-stable case, it's pretty, well, there is almost a proof, right? But there is a, well, almost, because at 2 we don't have it. Maybe, how much do I want to say, and how important is the rest? So, anyway, it doesn't. Let me just say that the methods that he uses are geometric class field theory, a theorem of Ihara, that's yeah, okay, so I'll write it down. Ingredients. So what I like about this proof is that it uses modern ingredients. So other people have tried to, we will see a bit later in this lecture that people like me also did things about these parametrisations, but they didn't use the things that he uses now. So so geometric class field theory, well, this is not so strange. A theorem of Ihara, he says the following, that if I can look at the Picard group of the special fiber, yeah, okay, so here is something I haven't said, but I have already used that you can look at this curve over Q, but of course there is no problem to do this over the integers. As soon as you have a moduli interpretation for your variety, I mean, then the moduli people have to prove that this has a moduli space, but once you have the moduli space, it makes sense over Z, right? So we can look at this over the finite field fp squared for some prime p. And this is now a curve over a finite field. Its Picard group is a finite group, right? Up to the degree, right? So let's say I take the elements that have degree 0, and we map to this so we take the fp squared rational points of this curve, and then we take only the supersingular points. So I should say something about elliptic curves in characteristic P. So this stands for supersingular. An elliptic curve in characteristic P actually has two possibilities. If you look at the number of, over an algebraically closed field, the number of torsion points of order P. Or the kernel of P, just as if you look at the points, is either cyclic of order P or just 0, right? Cyclic of order P is called ordinary, and this is what happens in almost all cases. And there's only finitely many supersingular elliptic curves, and so that's and this is a point on x0n is actually to consists of what? It's an elliptic curve and a subgroup of order n, right? But at least there is an elliptic curve, and you can it can be ordinary or supersingular. And there's only finitely many cases where it's ordinary. So this is a finite set. You take the free z module on that set. You take you take the elements of degree 0, so to speak, right? So elements in here are linear combinations of points, and you want the sum of the coefficients to be 0. And this gives you a degree 0 divisor. And the theorem that Ihara proves, actually he proves something much more general, but a consequence of it is that this is almost surjective. So he describes the co-kernel of this. So here we have something like sigma nd, where this, I should describe this sigma n, which is the Shimura group. Oh, well, why don't I make this go up a bit? Whoops. Oh. So, this Shimura group. Where we have the following. It's sigma n is actually defined to be the kernel of the map from J0n, say over Q to J1 of n, right? So remember that we have this, maybe I should say a bit more, right? So we have this x1 of Q, x1 goes to x0. Here we have an action. So the modular interpretation that I want to use here is that you have elliptic curves over schemes over Q together with an injective map, say I from the group scheme mu n over S. So the group scheme is this. So this morning we saw the multiplicative group. This is the scheme of nth roots of unity. So the kernel of multiplication by n on the multiplicative group into E. All right, this is and this should be injective. So of course there is an action. If you have such a map, you can compose with an automorphism of this group scheme, which is just an element of z mod n z star, right? The units modulo n. So here you have an action z mod n z cross. Actually 1 and minus 1 act trivially there, because if you compose this with minus 1, then this is isomorphic to the same thing, because minus 1 is also an automorphism of the elliptic curve. So you have this, and so standard things tell you that if you this is a quotient map for that action. So you can wonder, if I go from the Jacobian of this curve to the Jacobian of that curve, if I pull back, what is the kernel? Well, the kernel in general it's an abelian group. So if you have a group that acts here, it should at least come from the abelianized group, right? But it's already abelian, so that is, and it should come from the biggest unramified cover in there. So here you have, say, x something n, and here you have the biggest unramified cover in there, and here the group is, so this is, say, this sigma n dual, which is like just a constant group, and the kernel on the Jacobians is the dual, means Cartier dual. It's the home to the multiplicative group, right? And this is the kernel then, right? So Hira's theorem says that okay, anyway, it is a quotient of this one, and it's usually pretty small, right? It's so that is something very small. In particular, it doesn't depend on p. So if you take p very large, then it means that in this pk group you get almost everything by taking sums of differences of supersingular points, right? That is, so he uses that, and he uses also Hecker points of conductor e to the n for some prime n goes to infinity. I don't guarantee that it's the same prime. I don't think so, actually. So let's make that q to the n, all right? And work of Hida and Rubin. So, okay. So these are. It's interesting to see this preprint, and it indicates that you can do more by using these things. So, to the younger people, I would say parameterize with x1 and also use these kind of tools, right? So, actually, he also proves. So Watzau also proves. So just to convince you maybe more, that if you, so this sigma n is a subgroup that is a group of multiplicative type. So it's actually the dual of the Cartier dual of a constant group. So it's a group scheme over Q that has the property that if you take its Q bar valued points, then the action of the Galois group is given by cyclotomic characters. That is the point. And a group like this is called a multiplicative type group. For n square free, so if I kill the 2 part of this group, so the prime to 2 part of this Shimura group, this is the largest multiplicative type subgroup of odd order of J1 and Q. So this was proved also at 2, I think, by Maser for the case of n prime. Right? It's kind of the dual question of finding the rational torsion in there, for example. That is so this is the torsion subgroup, and the Galois action is via cyclotomic characters. So it's very analogous to finding the whole torsion in this Jacobian, and this is what Maser did. So he did both, right? He did the rational torsion and the multiplicative type for n prime, but by very different methods. I mean, so this seems to be more powerful now. Okay, so that is for this. In the time that I still have, I want to now talk a bit about Manin constants. This is also something, you won't see the Manin constant in the Birch-Swinnerton and Dyer conjecture, but it is still important because it gives the relation. With these modular parametrisations, you're looking at pieces of Jacobians of modular curves. And in the Birch-Swinnerton and Dyer conjecture, in this formula, you have the Néron differential of the abelian variety. But when you actually want to work with it, and you have your abelian variety as a quotient of the Jacobian of a modular curve, what you understand better is the normalized nu form that corresponds to this, say, to this elliptic curve. So you want to know how the two are related. Right? This is important, not for the conjecture, but if you want to prove things, I think William can say that you also want to know things about these Manin constants, because they compare the two. So well, now I have made my point for the historical error, and now, unfortunately, I want to refer to a lot of work that has been done on x0n. So I will let phi from x0n q to e be a strong modular parametrization. Fe times dq over q, the normalized nu form. Nu form. Right. And omega of e, the Néron differential. Right, that I have explained a bit before. Then, oh, actually, did I? Yeah, then there exists, then we have the following thing. You can pull back this differential phi upper star of omega e, right? It lives on e. You can pull it back, you get a differential form here. And because you know that this map, I mean, if you go via the Jacobian, this is somehow the Hecke operators on the Jacobian, the Hecke operator Tn on the Jacobian just induces multiplication by an here, right? An of this nth coefficient of this form here. This means that if you pull this back, you get an eigenform for the Hecke algebra with the same eigenvalues as this normalized nu form. And we have seen that this eigenspace was a one-dimensional space over the complex numbers, so also over the rational numbers. So this is C of E times f of E dq over q, if you like, for a unique C of E in Q star, right? And there is a unique rational number, non-zero, such that you have this thing. Now, and so if you know what this is, then you can compute. I mean, you can describe, in that case, this Néron differential in terms of your normalized nu form, of which you can compute all the coefficients in some way, right, by looking at the reductions of your elliptic curves. So, what about this constant? So it's called the Manin constant because I think Manin was the first to look at it, and there is the following conjecture by Manin. C of E is plus or minus 1, right? There is a... So that would simplify a lot. And I should say that there is lots of evidence for this because everything, all the elliptic curves that appear in Cremona's tables have this property. So that's a lot of them. On the other hand, I should say that, so let me formulate a question. What does this conjecture mean, right? I mean, this is maybe not a very precise question, but I want to stress that actually I don't have any conceptual interpretation of this. What does this conjecture mean? So the answer to this is that I don't know. I don't know what it means. So so somehow you could say that. So let me read. Answer. I don't know. So maybe somebody else knows. Right? That would be nice. But so intuitively, you would think the following thing, probably. You would say, okay, so So it's very important that this phi is strong, because if I just compose this with multiplication by 10 on my elliptic curve, then this would be plus or minus 10. Right? So it's important that you don't just do any parametrization. And the example with 11, if you look at it, it also shows that even if I ask that the kernel of the pullback is cyclic, it's not always 1 or minus 1. So somehow you can say, I take here, what have I done by taking this elliptic curve and not an isogenous one? So the strong parametrization is optimized for, I would say, for étale cohomology. Or say just, and what I mean by that is that the map it induces from H1 of my, say, modular curve, if I take just the ordinary homology with Z coefficients, this goes to H1 of E of C with Z coefficients. This is surjective. Right? In any case, for any non-zero map, you will get something of finite index here. But the fact that it is really surjective is quite significant. It means that there is only one way to do this, and this by taking this curve, E. So now, this Manin constant has to do with differential forms. So you would think, okay, then now look at the Ram cohomology. So, so intuitively, one would think that the conjecture means that phi is optimal for the Ram cohomology somehow, right? And it's not so far from that. So, and then when I mean the Ram cohomology, I mean this cohomology over Z, right? I mean, you have to somehow these differential forms, they give you the taste of the Ram cohomology. So, but it's not the same question, because it's not that, I mean, on homology, this would mean that you get, anyway, so you can, yeah, you could also go to the cohomology here by dualizing and working with coefficients mod p, and then the fact is that this will always be injective somehow. So with the Ram cohomology, you could think, okay, maybe it's that, right? That this has always to be injective when I pull back differential forms or the Ram cohomology classes from E to this curve, even if I reduce mod p. But there is, of course, problems with the places of bad reduction, because there you don't have a map from a proper curve to a proper curve. There are, and even the fact that this is plus or minus 1, it means something, so it's, it means something strange. It means that, so how do I say this here? Yeah, so the conjecture, yeah, I should say it like this, right? But the conjecture asks that phi upper star of this Néron differential is a generator of the sheaf of differentials on my modular curve, say now over Z, at the point infinity. This is, if you write down what it means, that this Manin constant is 1, it means that if you look at the Q expansion, right, that you have the first coefficient is 1. I mean the first, yeah. Because you know that this is going to be a multiple of that, and this one starts with a 1. So if this has to be plus or minus 1, it means that this should start as 1. And that means that at the cusp infinity, you get something like a generator, which is much more stronger. It's stronger than just asking that on the whole curve this generates a class. You are looking at what happens at one point, or at least in the neighborhood of this point, and there might be in the fiber mod p of this thing another component where it could just be a generator and 0 on the component of infinity. So really I should say I have no feeling what this means, right? I mean, On the other hand, you can prove a lot about this conjecture by just computing, right? But this is not very satisfactory. So maybe I should have 15 more minutes. So yeah, there is a. So I'm going to describe some results probably, and maybe also before I do that, the Stevens version of Manin's conjecture. So there is a Stevens version, and it looks better. But of course, I should say, also in that case, we don't know, or I don't know what it means, right? So Stevens version of Manin's conjecture. So it says the following: every elliptic curve. So this is much nicer, but every elliptic curve E over Q admits a phi x1 of NE Q to E such that phi upper star of omega E is actually F E times EQ over Q. So that's already, it looks nicer, but you cannot prove more about it. And also I'm going to indicate why, actually, do I do that? Yeah, I think so. So results, right? A. So for every phi from, say, one of the two versions, right? So this star is 0 or 1. And oh yeah, there is one thing also that I forgot, I think, to E. Let me just say this without writing. The moduli problem, oh no, I did say that, right? It was yeah, embeddings of mu n, right? So this is not necessarily the standard one. If you look in Katz and Maser, they will give you an embedding of z mod nz, right? And it's just a little twist, but it doesn't matter. But anyway, the point infinity should here go to 0. Yeah, and so for every map here that exists over Q, one has C phi in Z, right? So if you pull back the Néron differential, you get a multiple of the new form. Actually, I should say here n of E also. So you get a multiple, and at least you know it's an integer, right? This is also a bit consistent with what I said. You can always take a strong parameterization and then compose with multiplication by 100. Then your constant will be multiplied by 100. So, but anyway, it's always integer. This is good, and the proof is quite easy. But as there is little time, I will not do it. I will not permit myself the. How did Ursula say that? Je ne résiste pas au plaisir. I will resist, right? Because it would just take like 2 minutes. So maybe I'll write this up and then you can read it. It's just that you use the Néron property of the Néron model, and you use that this cusp here is in a part of the model over Z of this modular curve that is smooth over Z. That's all you need. More you don't need. So and this was published by Stevens for star equals 1 and by me for star equals 0. So, but this is very simple. Oh yeah, before I go further, I should also say that this was not so much known, and this has as a consequence something for computation, which is computationally of interest, that it guarantees that if you compute as Cremona does, starting from a new form, that you get a Weierstrass equation, but it's approximate. but it guarantees that these coefficients of the Weierstrass equation have to be integers. So you would only need to compute them with a precision of a half, or say a little bit better, a third, and then you have these integers, right? Before, these people were worried that it might look as an integer, but actually be a rational number that is very close to a much smaller integer. Right? But it's actually not the case. These coefficients are integers, and even you're supposed to find the minimal Weierstrass model if you do these computations. So each time people compute for these tables the curve, and they see that they verify that they got the minimal Weierstrass equation, they have actually verified that the Manin constant was 1 in that case. Right? So that is a good thing. Now, B. Right? So this is the first result. This is a general result, and it's nice. The two conjectures are related. So the one by Stevens and the one by Manin, because of the following. So if I suppose I look at this, right? So I have already said J0 NQ maps to J1 of NQ, and if I have the kernel is this Shimura group, finite group, and suppose I have here my curve E prime sitting in this Jacobian. So this NE is the conductor of E, by the way. And I can just look at the image in this one, right? I can just take its image and then see what the kernel is. But the kernel is just this sigma n intersect E prime, right? This is the kernel, and this cannot be big, because this is inside an elliptic curve over Q. You have a multiplicative type group scheme. That means that in the quotient of this elliptic curve by this group, which is also an elliptic curve over Q, you have the dual. Right? Oesterlé explained this. If you have an isogeny and it's dual, then the two kernels are Caché duals of each other. So that means that the dual of this group, which is a constant group, it's a group of rational points, is also in the Q rational points of the elliptic curve of this one, right? This is what you get by dividing out. So here you have sigma n intersect E prime dual, which is a constant group. So there is this list of Maser, which shows that this is very limited, right? You can get Z mod 2 times Z mod 2n for n up to 4, and then cyclic groups up to something like 10 or so. So it's really, so the difference, so actually the order of this intersection E prime is composed of the primes 2, 3, 5, and 7. So that means that for other primes, the questions are the same, right? So once we know that this number is an integer, the only question that remains is which are the prime divisors. And the only differences between the two things here are going to be primes like this. So that's only about the difference, right? We still don't know if no prime divides any Manin constant, because that's what we have to prove. But yeah, so more results. So this makes use of Maser, right? So maybe I should say via Maser. Right, Maser classified all the rational torsion on elliptic curves, so that helps. So now some more particular results. Consider now for phi strong, right? From x0n over q to e. So what do we know in this case? So we know that if P does not divide the conductor, so if the elliptic curve has good reduction at P, then P does not divide this Manin constant. And this is due to Mesa for p greater 2, and Abbes Humeau for p equals 2, and I should say plus Raynaud also, because they use a result of Raynaud that they include in an appendix. This is in the Eisenstein ideal paper, and this is in a Compositio paper.
What is isogenies of prime degree?
Isogenies of prime degree? Okay, good. Well, anyway, same Mesa. So there is a result that if p squared, so there is a slight generalization of this. P squared not dividing the conductor means that you do not have additive reduction, right? So it means that E is semi-stable. E semi-stable, not supersingular, right? I mean, semi-stable at P. This implies that, let me add this, and P greater 2. These two imply that P does not divide this Manin constant. And this is also due to Mesa. And there is a map, something at 2. 2 squared does not divide NE, right? This implies that 2 squared does not divide CE. Well, I mean, it's not as good as you would like, but you get, so this is Raynaud. So you see, the more difficult it gets, the worse the results become, right? So now there is my result. P greater 7 implies, well, actually this is a clear result, but P does not divide C of E, right? So I also say that the only primes where you can have a problem is at, primes smaller than 7 or less, right? And this I should say, so this was proved in 1992, but to my, I mean, still not published. And this is because I haven't finished writing it up. It's not because a referee is being hard or so. But it's, I mean, so maybe I should say something about the methods. So, yeah, I still have like a few minutes. So I had also prepared another proof, and I have to resist the temptation of presenting it. So what I should say is that to prove these results, the most important tool that people use is just the geometry over ZP of these models and things. So the main tool is the geometry. But sometimes you can, and yeah, this geometry becomes more and more complicated as the higher powers of the prime divide the conductor. That is the problem. So in this case, there is no, I mean, but P is bigger than 7, right? So we know for sure that P cubed will not divide the conductor of an elliptic curve, because this is so for elliptic curves. So if P is bigger than 3, then P cubed does not divide the conductor of an elliptic curve. So, but in this case, you have to study the geometry over ZP of the modular curve x0n, where P squared exactly divides n, right? So this n is P squared times something prime to P. And it looks very ugly. You can look in this book by Katz and Mesa what it looks like, and you can't do much with it. You have to extend, you have to work over some extension of QPs where this becomes semi-stable itself as a curve, and try to work from there, right? So that was, actually I did that more or less in my thesis. Actually, you can download my thesis from my homepage and read about it. But only that that was in '89, and I wasn't so happy with my thesis because it was much more complicated at that time. So I did more work, and now I still have to combine 2 papers into one and publish it. So the geometry is in every proof, actually. What else can you say? So there is some Stevens, well, I should say also here I using results of Stevens, using work of Stevens also, and he uses p-adic L function involving so special values of L functions. So this is another indication that somebody who wants to make more progress should look at that. look up Stevens' article. It's really very nice. And sometimes another tool you can use is looking at the complex numbers. Because, so let me write tools, geometry over ZP, and extensions. This stuff, right? And so analytic results over C. For example, there are formulas with the degree of phi, the conductor, this thing squared, and the value at s equals 2 of the symmetric square of your L function. There are formulas involving these things, and they are useful because they tell you how things should change when you twist your elliptic curve with something, and sometimes this helps. So actually my time is over, so this is the end. Yeah.